Safe fusion is an alternative to the sensor fusion formula for cases where you suspect that there is a correlation between the estimates. So let's repeat the sensor fusion formula. You have two different estimates, x hat 1 and x hat 2, and you can combine them to x hat if you know their covariances p1 and p2. But this assumes that the estimates are independent. So let's formulate the problem in the correct way when there is a correlation between x hat 1 and x hat 2. So we stack these two estimates on top of each other. We know that the expected value of this vector is x over x, because both estimates are unbiased. And we assume that we know the full covariance matrix, P1, P2 for the individual estimates, and P12 for the correlation. Correlation is the same as dependence for Gaussian distributions. But in general distributions, it's the second order properties we talk about, that is the covariance. So now we want to find a linear combination of the estimates that is unbiased. So we can postulate an estimate of the form L times x hat 1 plus I minus L x hat 2. By construction, this estimate will be unbiased. And then we are looking for the linear combination, the L, that minimizes the covariance matrix of this estimator. And this is a well-defined algebraic problem, and I leave the solution of this as a home exercise. But at least we have seen a constructive way to compute the blue estimator, the best linear unbiased estimator for this full problem. So in many cases you get information from many different directions, and your task in sensor fusion is to combine them. But in reality, these kind of information sources might be correlated. So in a way, if you are uncertain about correlation, it's better to have a conservative estimate, that is a conservative covariance, and thus with too large confidence intervals, than the reverse, to have too small covariance and too small confidence intervals. At least if you base a decision about your certainty, it's better to be conservative than too optimistic. And one conservative approach is to take either of the estimates. Then you certainly avoid double counting information. Safe fusion is an alternative where you combine x hat 1 and x hat 2 in a rather safe way to avoid being too optimistic. Here's the full algorithm. I will not try to explain all the details. It's a good exercise in algebraic manipulations using singular value decompositions and transformations. I leave it as a home exercise to understand this, but I will explain what it does intuitively using these three plots showing two transformations. The first transformation compresses one of the ellipsoids into a circle, so the red ellipsoid is compressed to a circle. And then we apply a second transformation that aligns the second ellipsoid to one of the axes of the parameter space. So in this figure, the blue ellipsoid is aligned with the second axis. Now we can compare each dimension of the parameter space separately. So we take the best information in the first direction and then the best information in the second direction. And in that way, we get the new ellipsoid aligned with the axis, the black one here. And then we can back transform to the original state space for the parameter vector x. As an example, suppose that we have two information sources, x1 and x2. These are fused to get x3, and x3 sends its estimate to the fourth node that combines x1 with x3. In this way, we have at x4 double counted the information from x1 that reaches x4 in two different ways. So we can compare the result of x4 with x5, which is the safe fusion of x1 and x3. And if we compare all three of them, we see that x3 is equal to x5. That's good, because then safe fusion gives exactly the correct result here, while x4 is too optimistic. So I urge you to download the Signal and Systems Lab from the homepage of this lecture series, if you have not done it already, and play around with these examples yourself to get some understanding and intuition. To sum up, safe fusion deals with the problem when you have two estimates x1 and x2 that are correlated. So P12 and P21 are not zero, as they are assumed to be in the sensor fusion formula. So the blue estimator for this full problem formulation can be derived, but in the course we just cover the case of the safe fusion algorithm that treats P12 and P21 as completely unknown and tries to make the best of the situation by computing a conservative covariance matrix and a conservative x hat by combining these two in using a series of transformations back and forth. Reading advice, check section 2.3.5 in the textbook.